Why ECU are the brain of the engine.
What we'll cover in this video is what is ECU, and hardware, sensors, and software.
Hi, I am Automan, and today in this video, we'll dissect the ECU hardware, inputs, outputs, software logic, diagnostics, plus common failures and tuning tips. I'll show clear diagrams and real troubleshooting steps, so by the end, you'll know how the ECU thinks. Every modern engine has a brain, the engine control unit, or ECU. It listens to dozens of sensors 1,000 times per second, and it directly controls fuel, spark, boost, and much more. Get this right, and your car runs smooth, powerful, and clean. Get it wrong, and you face poor performance, excess emissions, or an engine that won't start.
So what is an ECU? Before we proceed, let's get familiar with some of the glossary short terms. 1. AF or air-fuel ratio, mass of air to fuel. 2. Lambda ratio of actual AFR to stoichiometric AFR equals 1 is stoichiometric. 3. DTC diagnostic trouble code. 4. MAF and MAP mass airflow manifold absolute pressure sensors. 5. TPS throttle position sensor. 6. OBD-II onboard diagnostics vehicle standard. 7. PCM or ECM or ECU names for engine control computer. S.
An engine control unit is an automotive-grade embedded computer specifically designed to manage internal combustion and, in hybrid vehicles, portions of hybrid control engine functions. It performs real-time sensing and control the following.
Number 1. Deliver correct fuel or air for power, drivability, and emissions. Number 2. Control ignition timing. Number 3. Manage idle, cold start, and transient behavior. Number 4. Protect the engine knock detection, rev limit. Number 5. Communicate with other vehicle modules and diagnostic tools. Number 6. Store calibration and fault data.
Different vendors may call it ECU, ECM engine control module, PCM powertrain control module, engine plus transmission, or EMS engine management system. In modern cars, many functions that used to be in one ECU are split across several networked modules.
The hardware inside an ECU are.
Let's open the black box at a conceptual level. Inside an ECU, you'll find a microcontroller or CPU, flash memory for firmware and calibration maps, RAM and EEPROM for learned data, analog to digital converters ADCs for sensors, driver circuits for injectors and coils, high side and low side transistors, communication transceivers, CAN, LIN, and protection electronics for automotive voltages.
Let me elaborate these hardwares inside an engine control unit. To start with microcontroller CPU. Microcontroller CPU are automotive-grade MCU, frequently ARM Cortex family or other automotive MCUs. Real-time deterministic processing is required. Then comes memory.
Memory, ROM or flash, stores firmware and calibration maps. EEPROM or flash stores learned values or fuel trims, immobilizer data. RAM, runtime variables, and stack. Moving forward with analog to digital converters ADCs.
An analog to digital converters ADCs convert sensor voltages to digital values. Then comes digital I/O and PWM drivers.
These digital I/O and PWM drivers helps to drive injectors, coils, solenoids, motors. Moving forward to power supply and protection.
Power supply and protection helps to regulate voltage, transient suppression TVs, diodes, fuses, and protection against load dump, reverse polarity, and spikes. Next comes driver stages, power transistors.
These driver stages power transistors controls Injectors, ignition coil drivers, IGBTs, MOSFETs, idle motors, EGR, and VVT solenoids require robust drivers. Moving forward to communication interfaces.
Communication interfaces, Control CAN, LIN, FlexRay or Ethernet depending on vehicle, K-line ISO 9141 for older diagnostics. Here's a detailed elaboration of those ECU hardware design elements in an easy-to-follow format. 1. Communication interfaces. Modern ECUs need to communicate with other modules and diagnostic tools. Different interfaces are used depending on vehicle type, model year, and complexity. CAN stands for Controller Area Network, which most common in modern vehicles. High reliability, real-time communication, error detection, used for engine, transmission, ABS, airbags, etc. LIN stands for Local Interconnect Network, low-cost, simpler communication, often used for body electronics mirrors, windows, wipers, seat controls. FlexRay is very fast and deterministic time-triggered, and is used in safety-critical systems like advanced driver assistance, electric power steering. Ethernet, increasingly adopted for high-bandwidth data camera feeds, infotainment, ADAS, enables over-the-air OTA software updates. And K-line ISO 9141 older vehicles is legacy interface for diagnostics OBD-II, replaced largely by CAN in modern cars. 2. Crystal oscillator timing clock acts as the heartbeat of the ECU, provides a stable clock frequency for the microcontroller, critical for timing-sensitive tasks like fuel injection, ignition control, and communication synchronization. Automotive-grade crystals must handle vibration and wide temperature ranges. 3. Watchdog timers and safety circuits. Watchdog timer ensures the ECU firmware remains responsive. If the software freezes or runs into an infinite loop, the watchdog resets the system. 4. Enclosure and connector enclosure. Rugged housings protect electronics from dust, moisture, vibration, and chemicals. Many ECUs are potted filled with protective resin or conformally coated for insulation. Connectors, automotive-grade, weatherproof connectors, designed for vibration resistance, secure locking, and sealing against water or dirt, typically use gold-plated or tin-plated contacts for reliability. 5. Environmental robustness. ECUs must survive harsh automotive environments. The temperature range that ECU can withstand is rated for extreme ranges from -40°C to heat up to 125°C. It is critical for engine bay as ECUs exposed to heat. They are also protected from vibration and shock, so components are mounted with damping considerations, and solder joints are reinforced to prevent cracking.
In short, an ECU isn't just a small computer, it's a rugged, safety-certified, and communication-rich control unit designed to survive extreme automotive conditions while ensuring precise, real-time vehicle control. Now the input sensors. These are the eyes and ears of the ECU. I'll cover major types, the signal they produce, and the role they play. Major sensors inputs what they measure, and why these are the common sensors. An ECU uses crankshaft position sensor CKP used for engine speed and piston or rotation position. Essential for ignition and injection timing. Camshaft position sensor CMPN used for cylinder identification, sequential injection timing, valve timing sync. Whereas mass airflow MAF sensor measures actual intake air mass flow used to calculate fuel amount. Followed by manifold absolute pressure map sensor. It measures intake manifold pressure used in speed density systems. The throttle position sensor TPS throttle plate angle, driver demand and transient control. Then comes intake air temperature. It sensor senses air density correction and cold enrichment, whereas coolant temperature sensor XCTS detects engine temperature, cold start enrichment and fan control. An oxygen sensor O2 sensor lambda sensor, narrow band O2, indicates rich or lean around stoichiometric typical O1B signal, used for closed loop fueling. Wide band O2 WEGO, precise lambda measurement over a wide range, used in modern engines for accurate AFR control. NOx sensor listens for detonation or pinging so ECU can retard timing. Vehicle speed sensor VSS speed dependent controls, idle, cruise, some emissions checks. MAP or barometric pressure sensor altitude compensation. Fuel rail pressure sensor diesel common rail or direct injection gasoline controls injection pressure. Exhaust gas temperature EGT for diesel and turbo protection. Boost pressure sensor turbocharged engines boost control. Pedal position sensor drive by wire systems driver input to throttle control. Other sensors, such as EGR position, VVT position, ambient temperature, evaporative system pressure, steering angle for some torque-based controls are also present.
Actuators. Here their list of the things that ECU controls. 1. Fuel injectors. Pulse width is controlled to meter fuel port or direct injection. 2. Ignition coil spark control, ignition timing and dwell. 3. Idle air control valve electronic throttle by wire motor, manage idle and transient response. 4. Fuel pump relay priming, control fuel delivery. 5. EGR valve VVT solenoids variable valve timing, adjust valve timing. 6. Turbo wastegate or electronic boost control, manage boost. 7. Evap purge valve, secondary air injection, active catalytic heaters, emissions control. 8. Cooling fan relays and sometimes the radiator fan speed. 9. Solenoids for transmission in PCM systems.
Hardware is just one half, and the other half is software and calibration. The ECU stores lookup tables maps for fuel and timing, indexed by engine speed and load. The core fuel equation is simple. Fuel mass required equals air mass desired AFR. The ECU converts this to injector pulse width using injector flow rates, fuel pressure, and battery voltage compensation. The software is the intelligence and contains sensor processing 1, filtering, debounce, conversion from voltage or frequency to physical units, plausibility checks. 2. Maps and calibration tables, multi-dimensional lookup tables to D or 3D, fuel maps, timing maps, torque maps, keys, RPM and engine load or map, interpolation between table points to find precise control values. 3. Fuel calculation basic idea. Fuel mass needed equals air mass desired AFR. Convert fuel mass to injector pulse width using injector flow rate, fuel pressure, and battery voltage compensation. Closed loop control with O2 sensor adjusts short-term and long-term fuel trims. 4. Ignition timing calculation base timing equals map lookup, adjusted by knock feedback, engine temp, load, octane, and transient enrichments. 5. Closed loop control O2 driven closed loop lambda control to maintain stoichiometric AFR for gasoline with catalytic converter. PID or PI controllers used to adjust actuators, plus feed-forward terms for predictive control. 6. Adaptive learning long-term fuel trims, idle learning, adapt to component aging and environmental changes. 7. Knock control detic knocks, retard timing in that cylinder or region, attempts to protect engine while maintaining performance. Diagnostics and fault management. ECU sensor failures, calculate fallback strategies. Limp home mode, set DTCs and mill light. Safety and limp home. If critical failures occur, no crank or cam signal, Catastrophic fuel failure. Enter safe mode to allow driving to service center with reduced power. Timing and real-time scheduling tasks run with strict deadlines. Many functions are executed every engine cycle or multiple times per second, scheduling priorities.
Moving forward to fuel control details, stoichiometry and lambda. The stoichiometric for gasoline approximately 14.7 by 1 air, fuel mass equals 1. To meet emissions with a three-way catalytic converter, combustion near stoichiometry is required. Closed-loop operation. O2 sensor tells ECU rich or lean. ECU adjusts injector pulse to maintain 1 on narrowband or exact lambda with wideband. Open loop. Used during cold start, full throttle, or when O2 sensor not ready. ECU uses enrichment tables.
Next is ignition and timing control. ECU selects ignition timing from maps RPM versus load and modifies it based on follow knock feedback, retard, engine temp, cold compensation, octane knock, learning torque demand, transient enrichment, direct cylinder by cylinder control in modern sequential systems.
Moving forward to diesel and direct injection specifics. Diesel common rail. ECU controls rail pressure, multiple injection events, pilot main post, and timing with microsecond precision. Gasoline direct injection GDI. ECU controls injector timing at very high pressures with short pulses, can inject during intake or compression stroke for stratified charge.
Then comes communication and networks. Modern ECUs implement OBD-II diagnostics and store DTCs. When a critical emission sensor or circuit fails, the ECU will illuminate the MILCHECK engine and store codes. A scan tool can read DTCs, show freeze frame data, and live sensor PIDs. DTC's diagnostic trouble codes standardize POX codes, powertrain and manufacturer-specific codes, stored with status pending, confirmed. MILCHECK engine light, illuminated when emissions critical faults occur. Freeze frame, captures sensor state at time code set. Readiness monitors, emissions self-checks must be ready for inspection. Live data PID stream, scan tool shows sensor values, trims, fuel trims, misfire counters, etc.
Most common symptoms of ECU failure are 1. Engine won't start or misfires. 2. Check engine light on with multiple DTCs. 3. Intermittent stalling or poor idle. 4. No communication with scan tool. 5. Sudden loss of power, limp mode. And the typical most common causes are 1. Water ingress or corrosion at connector or potted electronics. 2. Overvoltage or load dump spikes, battery jump or charging faults. 3. Thermal cycling causing solder joint cracks. 4. Failed capacitors or power stage components. 5. Software corruption or failed firmware update. 6. Damaged CAN transceiver. 7. Immobilizer anti-theft mismatch after replacement. Here are some of the ways you can diagnostics pointers. 1. Check supply voltages and grounds. Most ECU problems are power or ground related. 2. Scan for DTCs and live data. 3. Check sensor supply reference, for example, 5 volts reference for stability. 4. Wiggle tests careful to reproduce intermittent faults. 5. Bench testing or replacement with known good unit.
Tuning modifies calibration maps to change fueling, timing, and boost. There are safe ways and risky ways. Always support hardware upgrades, fuel, cooling if you increase power, and beware of legal and emissions consequences. Reflashing must be done carefully. A bad flash can brick the ECU. Here are some of the repair, placement, and reflashing tuning tips. 1. Repair. Skilled electronics repair shops can replace capacitors, fix cracked solder joints, replace burned drivers. Some ECUs are sealed or potted and difficult to repair. 2. Replacement. Replacing with OEM requires correct part number, matching immobilizer or VIN programming, and sometimes dealer-level coding. 3. Reflashing, remapping ECU tuning. Changing MAP's fuel ignition boost to increase power or economy. Done with specialist tools. Bench flashing. Bootloader, OBD reflash. Risks: increased engine stress, emissions non-compliance, warranty void, immobilizer or VIN mismatch, possibility of bricking ECU. 4. Piggyback versus standalone. Piggyback intercepts or modifies signals, cheaper but limited. Standalone ECU fully replaces OEM ECU, gives full control, but requires complete calibration.
Here are some of the safety, standards, and reliability. 1. Automotive qualifications. Components usually AEC Q100 qualified MCUs and ECUs designed to ISO 16750 environment requirements temperature, vibration, electrical. 2. Functional safety. Modern safety critical functions are influenced by ISO 26260 principles, especially for drive-by-wire and advanced control. 3. MC or ME must resist wireless interference and not emit excessive noise. 4. Fail-safe and watchdogs. Software watchdogs and fallback strategies to avoid dangerous states.
Examples of ECU vendors' product families. Familiar names are Bosch, Denso, Continental Vito, Delphi, Siemens. Now parts of Continental or other firms. Magneti Marelli. These are large suppliers that make OEM ECUs and modules.
We hope you found this video helpful and informative. Don't forget to like, subscribe, and share it with others. Also, visit our website to explore a huge inventory of used OEM ECUs ready to buy today.